This is part 10 in a series of videos in which I'm attempting to repair this Wren executive computer. In the previous video I got as far as getting the startup screen to appear. There were some artifacts on the screen, if you recall, and that turned out to be a failing glue logic chip, so I've replaced that and now I get a good boot up each time, or at least as far as the welcome screen. However, it won't go past this screen. I don't have the actual boot disk in the floppy drive. I don't want to risk damaging it in case there's a fault with the system that could end up inadvertently writing to the disk. There is a blank disk, sacrificial disk in the drive at the moment, but the system won't know that it's blank unless it tries to spin it up and read it, and it's not getting as far as trying to do that. So in other words, there's a fault somewhere in the floppy drive control chain. And of course it could be anywhere. It could be in the drive itself, it could be in the floppy drive controller, or the glue logic that sits between the controller and the drive itself. So what we'll look at in this video is just doing some basic testing to try and determine where the fault may lie, and then we'll progress from there and see if we can get any further into getting this system fully up and running. Okay, so what I've done so far is I've got the analyzer connected to the Z80. It's monitoring the address and data lines. It's also connected to the read and write lines and the in-out request line. I've also got an input from the interrupt line, so we may want to look at those later on. And I've also got the analyzer connected to the floppy drive controller chip. It's looking at the data bus going into it, and it's also looking at some other potentially important lines that we may want to examine, including the interrupt. As you recall, the interrupt coming out of this device is permanently set, and it's causing a permanent active interrupt going into the Z80. Now that goes through a series of buffers and through a priority encoder and then onto the Z80. But it is originating from the floppy drive controller chip. So the way that line's supposed to work is when the floppy drive controller chip finishes its current task, it's supposed to change state on the output of that pin, and it's not doing anything. It's staying active all the time. So it could be a floppy drive controller chip, could be a floppy drive failure. I have tried swapping the two floppy drives over. There are two floppy drives in this machine, and to swap them over all you need to do is swap their physical positions on the cable and change the jumper on the drive. So I've done that, and I've set this particular drive to the master drive. I've tried the other drive as a master drive, and it makes no difference. It does the same thing every time. So you could of course start anywhere with fault finding this sort of problem. The fault could of course lie anywhere in the drive, in the controller chip, the interface between the Z80 and the controller chip, or the glue logic between the controller chip and the floppy drive interface. So we need to try and narrow that down a little bit and try to figure out what the fault is. I suspect it's the controller chip itself, but unfortunately I don't have a spare one to try. So we'll try to narrow it down before I order a replacement. So we'll start off by looking at some of the basics for the drive, and if we look at the controller chip pinout, the pins we want to look at initially are the step. That's an output that provides a pulse for every step that's required to drive the head position stepper on the drive. So every time there's a pulse out, it moves the stepper one position, and that works in conjunction with the direction pin, which determines whether the head's going in or out. And then there's also this TRO output. So this is an input, and this is an output from the drive, and this changes state when the head is over the home position. So in other words, once the head has driven all the way back and it's over track 0, then this line should go low. So to test this, what I'm going to do is manually move the head away from that position. The Wren is off at the moment, so the stepper shouldn't be locked. I'll manually move the head. I'm lifting it first, but even so this will probably damage the disc. I would say this is not the system disc, this is just a blank disc, but even so it should still try to read it. So this is just a sacrificial disc I'm using for this testing. I'll now power up the Wren, and what we should see is on channel 1, which is the yellow trace, we should see a series of pulses which are coming out of the step drive, and this is, as I say, what is used to drive the stepper motor on the floppy drive. And then the blue channel, the channel 2, is the status of the home position output, and that should go low once we reach the home position. And unfortunately you can't see the head, but I'll watch it and see if it does actually move. So I'm going to power the Wren up now. So as we saw, there were a series of pulses on the yellow channel, and then the blue channel went from initial high and it dropped to low once the head had reached the home position, and I can confirm that the head did indeed drive back to the home position. Okay, so I'll turn it back off. We'll try it one more time just to make sure that it's consistent. So I'll move the head away from the home position. I'll power the Wren back up, and again we see a series of pulses on the step line, and the home position output goes from high to low once the home position is reached, and again the head did indeed drive back to the home position. So that part of it's working, so we know that the chip is working to a certain extent. So the next thing I want to do is look at the IP output from the drive. So I've moved channel 2 probe over to that pin, and this is the output from the drive that gives a pulse every time, or changes state every time the sector hole in the disc is encountered. So if you know how these drives work, you know there's a small hole in the floppy disk itself, and there's a sensor that senses when that hole passes by, and it's used so that the drive can determine where in the rotation of the disk it is, so it knows which sector's which. If I now manually, I'll turn the Wren back on, if I now manually change or rotate the disk drive motor, we'll see that as the hole is passed, that the line drops and rises again. So in other words, that output's working fine. One final thing I want to check is the Wren Part10 output. So if I move the jumper up to the next pin, so this is the Wren Part10. This is the output that changes state when the protection tab on the disk is either present or not present. So on this disk it's removed, so it's not writable. But if I just pop the disk out, then because it's a notch in the side of the disk that's allowing the sensor to detect the notch, then just by moving the disk out of its fully inserted position, this line should change state. So I'll just pop the disk out, and as we can see, this has changed state. If I push the disk back in, that should go high again, because obviously the notch in the disk will then be aligned with the sensor again. I push it back in, and as you can see, that line is working as well. So this tells us a few things. It tells us that the floppy drive is basically working. It doesn't tell us how well it's working, but it just seems to be capable of going through the basic motions. So the next thing we have to do is start looking in more depth at the driving of this control chip. Now in the previous video I mentioned that what I had been doing by way of testing was to look at the in-out ports on the machine, figure out what the address of each in-out port was and how it related to the various devices. And I was doing that by putting the logic analyzer onto the device, or at least onto the address and data bus of the Z80, and then putting another input onto the enable line for the particular device I was investigating. I've done that with the floppy drive controller chip, and determined that it's at address 28, and we'll look now at the analyzer and I'll show you how I determine that. Okay, so on the analyzer I have it hooked up to the DAL, which is the data bus coming into and out of this floppy drive controller, and I've got that identified as DAL on the logic analyzer. I'm also connected to the A0 and A1 lines, and I've got that labelled as A0, A1, although I'm looking at that as a single bus rather than individual lines. I've got INTRQ connected, which is the interrupt output from the controller chip. I have chip select, which is the chip select. I've got write enable, read enable, and I've also got read and write on the Z80 as well that we can capture. Next thing is to set up a trigger and see what we're interested in. In this case I just want to look at the chip select line that's controlling the floppy drive controller. The only one we're interested in is chip select, and that's now ready to go. So we'll run the analyzer, and because the Wren's already running and it's constantly looping round trying to address that device, you can see we have captured some data. I'll run it again and we're capturing the same thing every time. So what we're looking at here is the top blue trace is the Z80 address bus. Now you can quite easily equate this to the actual listing. If you recall, I did a disassembled listing for this, and this includes the addresses, and if you look through the listing you can find out where we are. Here we're at address 90AA. Jumps around a bit, of course, as any code does. But what we're interested in here is the chip select line for the floppy drive controller chip, and that's the blue trace that I've labelled /CS. And when that goes low, the floppy drive controller chip is being accessed. And if we look at the bottom, we can see the read enable line for that device as well. So in other words, at this point we are trying to read data from the floppy drive controller. The A0 and A1 inputs, if you recall, there are two inputs to the chip. They determine which particular register within the floppy drive controller we are reading from or writing to, and we'll come back to that in a few minutes. But what we're interested in here is trying to figure out where in the in-out map the floppy drive controller chip actually is. And this method is how I determined where all the devices in the machine are. And what I end up with is a fairly detailed document that I can use for future fault finding should I need to repair one of these machines again. Schematic would be far easier, but this works fairly well, and it's probably nowhere near as time consuming as it may appear to be. So what we've got now is, on the top row, the address line, we have the address here at AB is the instruction address that we're currently executing. The 28 on the data bus, and you can see here on the address bus we've got a value of 0828. Now if you recall, on the Z80 the in-out instructions operate by putting the in-out port address on the lower 8 bits of the address bus, and that's what's happening here. 28 is the lower 8 bits of the address bus, and this is occurring during an in-out operation. Now I have previously, when I was doing this initial testing, I was also capturing the in-out request line on the Z80, but because it won't all fit on the screen I've removed that. But if you look through this, again, if you look at the code at these addresses, you'll see that it's this is actually an in instruction that's being executed. And if you do this with all the devices on the machine, you can very easily determine what port certain devices are on. So in this case we know that the floppy drive controller, at least this particular part of it, is on port 28 hex, and it's both input and outputs. In other words, the same port is used for reading and writing to the registers within that device. What we can then do is go back to trigger and set the address that we want to trigger on. And in this case, although it's not really a memory address we're triggering on, it is the address bus that we're triggering on during a read or write operation on the in-out port. So if we set it to don't care, because we don't care about the upper 8 bits, but the lower 8 bits we want to set as 28, because that's the port that we now know we're interested in. So in other words, anything we capture on this now, if it's part of an in-out operation, is an in-out operation relating to the floppy drive controller chip. We can then go back to waveform and run again. Although we're getting the same data, we can now go through and look at different parts of the code, and we can also determine if the machine is ever writing to or reading from the controller chip. So we go back to trigger, and let's say that we want to check to see if it's ever being written to. If we set the write enable or the write line to 0, now I'll stress here that the write line is the Z80 write line, and again, if you're not familiar with the Z80, then when it's performing in-out instructions, it uses various pins so that the system can determine whether it's a memory write or read or an in-out write or read. And to do that, it uses a fairly simple mechanism. So looking back at the pinout for the Z80, we have the in-out request, and that's used to tell the system that this is an in-out request rather than a memory read or write, and it goes low when it's an in-out operation. In other words, when an in-out, in or out instruction is being executed, this will go low, and then the system will look at the read or write line to determine whether it's a read from the in-out port or a write to the in-out port. This is normally done in conjunction with the M1 line so that the operation happens at a sensible part in the machine cycle. But so that's essentially how the system determines whether it's a write or read from or to an in-out port. And what we're looking at here is whether the Z80 ever tries to write a value to the floppy drive controller chip. We'll then go back and we'll arm the analyzer. As you can see, nothing's happening so far. I'll try resetting the Wren and nothing happens. So in other words, it never seems to be trying to write anything to that device. It's a bit odd because I would have expected it to write some configuration information, but we're not getting very far through the boot up sequence, so that possibly is to be expected. If we were seeing activity here but the drive still wasn't responding, then it might be there was a disconnect between the write output of the Z80 and the write input to the floppy drive controller, and we could then monitor the pin directly on the controller chip. But because there's nothing happening at the Z80, then there's no point as going as far as looking at the floppy drive controller itself. Okay, so if we go back to trigger, I mentioned that we have this A0 and A1 line. What we can do is look at which particular registers the Z80 is trying to read from. So whether it's trying to read from a data register or a control register. Now that's fairly important because, as I said, the interrupt is constantly set, and it shouldn't be. It should be clearing and allowing the Z80 to move on. And we'll come back and look at that in a bit more detail later, but one thing I have tried doing is lifting that pin on the controller chip, waiting for the boot up screen to ask me to put the disk in, and then I've manually triggered an interrupt pulse I won't show it because it's kind of a long-winded thing to do, but what happens is on the screen it tells me it's not a system disk, but the point is it does respond and give me a different message. So in other words, the Z80 is still running and it's still able to respond to what the controller chip is doing. So what we'll do now is we'll just have a look at the data sheet and see which particular address the Z80 is trying to read from. So we'll just go back to trigger, turn the write back off so that we can get some data. So we've got some data. We'll look to see what the register 0 is. So you can see that A0, A1 is set to a value of 0. So I'll just grab the data sheet and we'll see what register that should be. Okay, so we can see that the value on A0, A1 is 0, and if we look on the data sheet we can see that address 00 is the status register, and if it's a read, it's a read of the status register. And if we then look at the operation of the interrupt output pin, we can see that what's supposed to happen is this should be reset whenever the status register is read. And we are indeed reading the status register. These are the lines going into the controller chip. But as you can see, the green line is never changing. And this is the output interrupt line from the floppy drive controller. So in other words, although we are going through the read operation of the status register, it's not clearing the interrupt, and the interrupt is staying active, and the Z80 is never getting the message to move on to the next step, which I suspect is why it's not getting as far as writing any configuration data to the floppy drive controller chip. So I think it's I think what's supposed to be happening here is once the head has driven back to the home position and the ready line has changed state, I think the interrupt line should be released, and then the Z80 should move on to the next step of the floppy drive controller chip configuration. But that interrupt line is never changing state. So it does look fairly certain that it is a failed floppy drive controller chip. So I'll get one of those ordered, try swapping it out and see if that corrects the problem. In the meantime, if anyone's come across this fault before and knows what the likely cause is, then please let me know. I've turned the logic analyzer off so you can hear me. There's just one thing I wanted to touch on and expand on a little bit before I finish this video, and that is this in-out map addressing that I've been mentioning. The techniques I use can be quite powerful, especially if you don't have a schematic for a fairly complex system. And I thought I'd just explain in a bit more detail exactly how I go about doing this, in case anyone was interested in the details of how I use the analyzer to determine the in-out mapping and port addresses. So firstly, just to recap on the way the Z80 handles in-out. If an in or out instruction are executed by the Z80, then it responds by putting a low value onto the in-out request line, and it will also, depending on whether it's a write or a read, it will lower one of the two write or read lines, and that way the system the Z80 is running in can decode the in-outs as being an in instruction or an out instruction. In addition to that, the system of course needs to know which particular port or address the device is going to be accessed through, and that's simply done by the Z80 in response to an in or out instruction, putting the value associated with that instruction onto the lower 8 bits of the address bus. So if we look at a typical instruction, we have here out 3BA. So when this instruction is executed, the Z80 will respond by lowering the in-out request line. It's an out instruction, so it's a write, so it will also lower the write output. It will then put the value of 3B onto the lower 8 bits of the address bus, and then it will copy the contents in the Z80A register out onto the data bus. So that's how an out instruction is handled. In instructions are handled in a very similar way, so we have one here in A39, and this works in the reverse way, that when this instruction is executed, the in-out request line will again go low because it's an in or out instruction. The value of 39 will be put onto the lower 8 bits of the address bus, and the contents currently on the data bus will be copied into the A register. So okay, how does that help us determine the in-out port mapping? Well, what we can do is look at how the devices are being addressed. So if we take the device we were looking at earlier, the floppy drive controller, we can hook up the logic analyzer to trigger on its chip select line. So when that line is active, in this case low, we know that this device is being accessed, and we can then look at the value on the lower 8 bits of the Z80 address bus, and that will give us the port value. Now the only complication here, and what you'll notice if you look through maps like this, is they tend to appear in groups. And the reason for that is because in general when you design a system, you need to decode the individual registers within a particular device. So if we look at the pinout for the floppy drive controller, we see that there are 2 pins used for register selection. And then if we look at the datasheet, we can see that there are actually 4 sets of registers internally that we need to try and access, and they are accessed by whatever combination we have on the A0 and A1 lines, and that in conjunction with whether we are performing a read or a write operation. So we need to decode this in order to be able to read from and write to this device. Although they're labelled A0 and A1, you don't necessarily need to use A0 and A1, but it is convenient to use consecutive addresses most of the time for a particular device. And that's why we have a block of addresses for this particular device. Address 28 is the first address, and so if we then imagine that address 0 and address 1 are both 0 when we access that particular device, then to access the next register in that device we would simply use address 29, and then to access the next one we would use 2A, and then to access the next one we would use 2B. And that's exactly what we're seeing on the map. We're seeing 28, so that's our base address for the device. So that would be, if it was binary, it would be 101000. And then to access the next register, we simply set address line 0 to a 1. That gives us 29. So in other words, this is a small block of 4 addresses that give us the decoding for these 4 registers within this device, and then we can just determine whether we want to read and write to both of those. And as you can see here, we don't always read and write. Sometimes we only ever want to read or write to particular addresses, but either way the decoding will work the same. So for the floppy drive we have 2 registers that we want to both read to and write from, and 2 that we're only interested in writing to. Okay, so that's how the decoding works on this particular machine. It does vary from machine to machine, but generally speaking you'll see addresses in blocks, and that tends to reflect the number of registers within the device, and that gives you even more clues as to what particular device it might be based on the number of bits. So for example, we know that in this particular machine there are 6 bits used for the address bank decoding, and if we look, there is only one block of 6, so we kind of already know what the base address is for the bank or bank switching within this machine. And you can go through, and generally speaking, you can on a machine that's not too complex like this, you can generally just at a glance figure out what's going on. For example, this one there's only 2 registers, on this one there are 3, so you can get a lot of information just by looking at this. So hope that made sense. If it didn't and you want me to go over this in more detail, then leave a comment, but this is a very powerful technique, and if you do have a logic analyzer and you want to spend maybe half an hour going over the board and determining what all the addresses are for the devices, it can save you a huge amount of time. And then when you come to look at the disassembled code, you can pretty much immediately read it to see what it's saying. So for example, out 01, you know by your map that it's going to be this particular device. So again, hope that made sense. If not, let me know and I'll go over it in more detail.